we turn our attention to energy. And it is not an overstatement to say that the appropriate use of energy is by far the most important challenge facing both the United States and the world. The international energy imbalance is staggering. There are very few countries that are using most of the current energy sources. The US, European Union, China, India. Although the US is only about 5% of the world's population, we account for nearly a quarter of the oil consumption. And in 2011, we imported about 48% of our oil needs, less than half. This was deemed as a success. And the energy picture is changing rapidly in the United States, thanks in great part to the introduction of fracking and natural gas as a source and a substitute for imported fuels and for coal. World energy consumption is going to keep going up, though, almost 60% by 2040, and it won't so much be in the industrial nations such as the United States and European Union. It's going to be in those high growth areas, China, India, Brazil too, and the U.S., just to give you some idea, the U.S. was the biggest energy consumer for more than 100 years. China overtook us in 2009, and they are about 5% higher. And this is even more staggering when you realize that as recently as 2000, the U.S. consumption was double that of China's. This is another way that this is measured, and this is how they're doing it now on most of my government sites. The OECD is a collection of nations formed after World War II. They had to be democracies. They had to be capitalistic, and they were a replacement for the first world, third world kind of designation. But the non-OECDs, those are the countries that are growing or developing countries in the last 50 years. And it's the BRIC countries, especially Brazil, Russia, India, and China. And their demand's going up, 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 up. Let's talk about what we consider fossil fuels. We have heard this term forever, but there really are three basic fossil fuels, one in each phase of state. Oil is our liquid. She's expected to remain the dominant source of power in the world at about 36%. Coal is extremely important because it is by far the most abundant fossil fuel at 85% of known supply. It is our solid, so that 85% is by mass, by the way. So that does change a little bit. The problem with coal is it's incredibly dirty, incredibly impure. Natural gas is growing the fastest and has been for a while. It is primarily methane, CH4, but it's a mixture of some smaller hydrocarbons as well. It burns the cleanest. It still produces CO2, one of the most important of the greenhouse gases. And it's important to remember that methane itself is a much more powerful greenhouse gas than CO2. So as they do this, the interests in oil and natural gas, they have been working with the EPA to make sure that they release as little as possible natural gas into the atmosphere as they procure it. It is not enough for some people, but it is moving very fast in their development of what they call green taps. Renewable and nuclear, they are rising, yes, primarily, renewables, as of 2010, they're at 11% internationally, and they're thinking they'll go up to about 15% by 2035, 2040. They're going to stay low. And nuclear interests, they are rising, and again, primarily in China and India, although rising. France, surprisingly, gets most of it, I mean, over 80% of its electricity from nuclear. And they still, though, internationally, they're only at 5%. In the next 30 years, 25, 30 years, they're expected to go up about 7%. So not a huge increase. Okay, here is a more breaking down the different kinds of materials in a more recent production or in more recent measurements. Look at where the source is. The Energy Information Administration, the EIA, that's a very important source for information. That's part of the Department of Energy. And if you want to find tables of very important facts, this is the place to go. And they've done a very nice job online. So I would encourage you to become familiar with it. The liquid fuels are expected to stay there, go down a bit. Natural gas go up. It's less carbon intensive than other fossil fuels, more efficiently burned, higher fuel value. But coal use is expected to increase in China and India. It is the cheapest, but it is nasty stuff. We'll talk about that later. The thought is that this is an overestimate of what coal consumption will be in China and India because it does pollute the air so much, and the populace is suffering a great deal, especially in urban China. Renewables, again, they're going up. They're fastest growing, but that's all relative because when you think about the overall amounts, they're going up by the most percentage points, but they're so small that, All right. And then nuclear is increasing as well. All right. Let's talk about what energy is. And a very simplistic way of looking at it, but it's also very true, energy is required to do something that won't happen by itself, whether it's thinking of a bright new idea or cleaning your closet. Let's organize our energy. Let's look at the different forms of energy, and one is organized. That is the capacity to do work, to do something useful, electrical, mechanical, chemical, push something, make electrons dance between different reactants. And randomized energy is heat. It's often thought of as wasted energy. It is the result of random molecular motion. The units for energy. The calorie C, the joule J. One is the one we're very familiar with, especially for our food. The other one is a joule is more common in scientific endeavors. You can easily relate them. 1 calorie equals 4.184 joules. And they're so teeny, we usually work in increments of 1,000. Kilojoules or kilocalories. And you see that kilocalories over there? That is the same as a dietary calorie, written as a capital C. CAL is 1,000 little calories. Energy comes, though, in two camps. We have kinetic energy, which is the energy of motion. And then one that's very important to us in chemistry is the potential energy. This is, you've probably seen it as a consequence of like a ball sitting on a ledge or a ball rolling down, sitting on top of a incline, and it's got total potential energy sitting on top there, and then you start down the incline and the potential changes into kinetic. That's the old demonstration. For us, I want you to look at the other one, composition. And this is really important for us because in chemistry, it's the energy stored in chemical bonds. And chemistry, the most interesting thing to us in chemistry I've mentioned is the reaction of chemicals. And a reaction means that I'm breaking bonds in the reactants and forming new bonds in the products. Okay, let's just look at, for example, a power plant, a coal-burning power plant. And we end up with electricity in our homes from that. Power plants are inevitably inefficient, 63% to the house, 15% to the lamp. Think about your old-fashioned incandescent bulbs. 15% of the energy from the power plants is making it into light. The rest is lost as heat, which you probably know very well if you've ever touched a light bulb after it's been used. I need you to know this. The first law of thermodynamics is very important. Energy is neither created nor destroyed, but may be transformed from one form into another. And I think that this, if you talk to the man in the street, they don't appreciate this. They think that energy easily can be created, destroyed. For example, lighting a fire. You are changing potential energy of the logs into heat energy and light energy of the flames. It's the same amount numerically, but is just been transformed from one form into the other. The zeroth law, by the way, is that if you have two bodies in contact, they will transfer heat from one to the other until they come to the same levels. All right, taking random thermal energy and transforming it into ordered work against the Taking random thermal energy and transforming it into ordered work goes against the second law of thermodynamics. The second law of thermodynamics, that's in the box at the bottom, is the entropy of the universe is increasing. Entropy can be also deemed disorder. And what this is saying is, in the natural order of things, the disorder of the universe must always be increasing in any kind of process. So the potential energies in the chemical bonds, we burn them. And the reason why we burn coal is to boil water. The heat energy boils the water and creates steam. The steam goes to turn the turbines. And the turbines, that's mechanical energy. When you turn these propellers in a magnetic field, you'll produce electricity. And electricity is sent down the wires to our homes. So all of it does not convert into the potential energy of the chemical bonds does not all transfer into the electrical energy into your light bulb. So we've got energies now that are created or destroyed. So you're losing it from useful to non-useful. Some of it is lost to resistive heating, and some is just lost to heat to the environment around. And overall, you are losing a huge amount here. But all right, and the next thing we're going to talk about is chemical reactions, how we can quantify that loss.